really Maxwell-Boltzmann, right? And I'm going to do we did Rayleigh and we did Gaussian. I'm going to do Maxwell-Boltzmann today. Going to do the exponential. I'm going to do the actual probability density function that is uniform. Yeah, go ahead.
Well, I just had a question.
Go ahead. Which one?
261.
Let's. Well, I want to do some of these because honestly, discussing them helps. 2-6.1. Is this the exercise or the actual problem?
The actual problem.
Go ahead. What does it say? You may be wrong, by the way.
A Gaussian random current having zero mean
All right, hold on. That means the current has a zero mean. Go ahead.
and a variance of 4.
Sigma I, variance of 4, and that means sigma I is equal to 2. Go ahead.
His fast through is resistance of 3 ohms.
All right, so these are fun ones. These are Rayleigh distributions. So you got R equals 3 ohms, got a current I, and they want to know power or something, right?
This is the find the mean value of the power dissipated.
All right, so now these things, you got a squared law device. Power is proportional to I squared, right? So first, define power in the resistor is I squared times R, right?
Mhm.
Now, what do they want to know about the power?
The mean value of the power dissipated.
All right, so the mean value or the expected value of the power dissipated, I'm defining that P as power. It may not be the best choice, but that's what I'm using.
Yeah, they use W.
Okay, we can use W. We can use W. You're going to see something real quick here. It's not bad. We'll use W, which makes sense in watts, right? That's really, R is a constant, right? So that's really R times the expected value of I squared, correct? Isn't that the mean squared value of I? So what we want is the mean squared value of I. It's got zero mean, right? What is the mean squared value? If you think about this, think about it, hold it. Remember, sigma squared is equal to, normally it's x squared bar, and then it's going to be, minus x bar squared, correct, class? Just, I'll let you take a second. I want to make sure I discuss this thoroughly because there's subtleties that can confuse people if you're not awake. Okay. All right. Now, now I'll put it in terms of current. So sigma squared of I is equal to I squared bar minus I bar squared, which is 0, correct? That's what they say, correct? Therefore, if I look at this, by definition, I squared is sigma I squared, and that is 4, correct? I hope that's the answer. I mean 4 for the I squared value, then for the power, we're going to have to multiply by the resistance. So this is going to be, what was the resistance, 3?
Yeah.
So it's 12 watts.
Yeah.
Oh. What? I mean, that's all it is, right? What else?
Find the variance of the power dissipated.
Okay. How do you find the variance of the power dissipated? And this is just one of those things where this is the power, right?
Mm-hmm.
All right. So that's the mean square. Or if I look at this, this is the mean squared value of the power. It's the mean value of the power. All right. So how do you find the mean squared value of the power? Just think about it. What is that? That's the expected value of W squared, right? That's the expected value of what? R squared I to the 4th, correct? I'm just trying to be clear about this. I don't know if he does it this way.
Yeah, he does.
You all with me on this, class? Did you all take a look at these?
Yes.
It's straightforward if you think it through. So I can take the R squared out in front. Now what's the expected value of I to the 4th? It's the what? 4th central line? I mean, actually it is. Well, no it isn't. Because what? The current has a mean of 0, but the power doesn't, right? So this is what this is going to be, which equals to what? And let me put it down here. So we have R squared W squared bar is going to be equal to, and this would be sigma of W squared plus W bar squared, right? And they want, they want,
The variance of the power.
that's that, right, for power. So, if we go there, what would it be? So, that's expected, what is the expected value? I need this, right, of I to the fourth.
Why is it a plus?
Huh?
Why is it a plus right there?
This right here is mean squared. It would be like, if I take x squared bar, that's sigma squared of x plus x bar squared, right? Now if I take sigma x, then it's gonna be x bar squared minus, x squared bar minus x bar squared, correct, class?
Yeah. Okay.
Okay, I hope I'm saying this stuff in a way that's not confusing. So how do you get the fourth moment? Better yet,
The fourth moment?
of I to the fourth. I is Gaussian, is it not?
3 sigma
Three
to the fourth.
It's what? This is the fourth moment though. No, fourth second moment we can get.
This is a
The
fourth.
mean to the fourth 6, mean squared.
Now this is Gaussian, that's where you can use this, right? All right, so the fourth moment, and the I has a mean of 0, correct, class? So that's gonna be what? Normally it's 1 times 3 times dot dot dot, n minus 1 times sigma to the n. You remember that formula? All right, so for ours, it's gonna be what? That's gonna be 1 time, because that's 4, so it's gonna be 3 times, and it's gonna be, what is sigma of I? 2, so it's 4 squared, so it's gonna be 4 squared, so that's 16 times 3, or 48, and that's gonna be for this, and then if we come over here, and we want, let me do it down here. Do y'all follow me what I'm doing here? So if I take a look at the expected value of W squared or the power squared, I'm sorry. This is the mean squared value of the power, pardon me. Let me say it that way. That's going to be equal to, and here, the way I did it, I have R squared, the expected value of I to the fourth, which we got there, fourth moment. So that's going to be 3, right, squared, and this is going to be, what is that, 48, let's write the whole thing down. And that is equal to sigma W squared, which we're going to calculate, plus the mean value of the power squared, which is 12 watts squared. So that means, you can tell me what this is going to be 9 times 48 minus 12 squared, or 144. What is that? That's the variance, though. Standard deviation squared. What did we get for that?
288.
Is that correct?
Yeah.
288? And then I guess we might as well get the actual standard deviation of power. Square root of that. 288 square root. Anyone? I hope this. I don't know how we did it.
16.97.
All right, is that the right 16.97? Does he have that answer?
No, I mean, he doesn't ask for it.
You didn't ask for
Does
the.
he ask for this?
Yeah, just the variance.
Just
Is that right?
yeah.
But that's the way I do it. But the real thing with these squared problems, you got to think it through. I mean, anytime you have a squared law device, because what would I'm going to ask you this. So I'm just seeing how you think about this one. This was covered last lecture. I'll do it over here. So I want the probability that the power is greater than 1 watt and less than 20 watts. How do you get there?
I mean, that's kind of like the next part.
What?
Kind of like the next part.
There's the next problem.
Yeah, it's
All right, but what are you gonna do? Then you're gonna define, I would define that in terms of the current, right? What else could we do? Well, we could get the probability density function for the power, right? Remember last time in a quiz, right? You got that f of y, but I didn't do it that way. I used f of x and just found the bounds on x. Do y'all remember that?
Yeah.
Now that's the way I do it. Either way is acceptable. Let me erase this.
Oh, I got a quick question. So, what was the purpose of doing the, see what you have up there on the top right? You rearranged the variance equation to have r squared.
What do we after this, right?
Well, I thought we were, yes, sir, yes,
Okay,
we
so
are after that.
in order to get that, we've got that, and we need this, right?
So you just did that so that we could see that we need I.
We need r squared, and then we need the mean squared value of,
Well, r squared is a constant.
sorry, this is I.
Okay.
I'm sorry. I'm
Okay.
so sorry. I'm glad you said it. That should
I-
be nice. Yeah, it's,
Oh,
that's on me.
I did the fourth, right?
Huh?
That's I did the fourth, right?
Yes.
Okay.
I am very sorry about
Okay,
this.
that makes sense. So then that just shows that we need that, and then you went there and solved it. Okay.
Yeah, I'm sorry. I'll try to be more clear. That's my fault. I'm being a little sloppy with this one, but the truth is this one, you define the unknown variable, in this case power, in terms of the known variable, the one given with the random or with Gaussian probability.
Yeah.
So power is r times I squared. Define that. Then the expected value of any of the terms with r times I squared is going to really be in terms of the expected value. You're going to get an r squared or an r times the expected value of I squared or I to the fourth. I'm sorry if I didn't make that clear.
Yeah, that makes
I'm sorry about that. Let me erase this and we'll do the next part, okay? Is there anything going on this week or this week in campus or anything? Art
Father's
show?
Day this week.
Huh?
It's Father's Day this week.
Yeah, but I mean, I suppose, last weekend they had Opelika had this big festival downtown of all sorts
Yeah,
of,
Art Walk.
yeah.
It was pretty cool. They
Last
had
week, last week.
That was last week, yeah. They had a steel drum band that came out.
So what is this, is there anything this week? This is the summer, they usually have something, this Thursday will be an open market over there by the Red Barn for the, the Ag Heritage Park is
Yeah.
downtown.
Like a
Okay.
farmer's market?
They'll have, it'd be local farmers market, they'll have organic foods sometimes, they'll have a lot of good stuff, but it'll be, I think from, 1 or maybe 2 or 3 till like 5, but you can look at the times. That's really good produce and it's local and a lot of it's organic, so it's pretty healthy. Or some of it is organic in the past, but you never know when you go there. The thing is, they got fresh melons and all that stuff.
3 to 6 on Thursday. That's tomorrow.
Yeah, and I go there. What I do is I go fishing.
Is there some good fish in that pond?
Not good, but I mean, you're not gonna find a trophy bass in there, but just have fun with a fly rod or something, goofing around.
That's a good place to fly fish because there's no trees.
That's right. Plenty of dogs though. That's one thing.
Yeah.
Okay, so next part, go ahead.
final probability that the instantaneous power will exceed 36 watts.
So this is part 6.2, right? Or is it
This is still 6-1.
6.1? Okay. So how do you do this? They want the probability, right? That what?
The
The
instantaneous
power is greater than what?
36.
How do you do it? Now, I'll tell you how I do it. I don't know how you do it, but this is how I do it. I take a look at this. Here's power and here's current, right? Power is equal to Ri squared. I take a look at that and I can see it does something like this if you actually graph it, right? So the probability that the power is greater than 36 watts, now I define power, that's power in watts, is equal to I squared R. R happens to be 3, right? So that means W over 3, and then I take the square root of this, plus or minus is equal to I. That's the threshold. I'll either be above or below. You with me on this, guys? Did you do it this weekend? Did you do it the other way?
Basically, yeah.
You can do it by getting the density function, but it's easier, in my opinion, to do it this way. So when I take a look at this, 36 watts, right?
Okay.
So this is gonna be plus or minus the square root of 36 by 3 equal I, that's the threshold points, right? And what is that? That's gonna be 6, huh? 6 over square root of 3? What is, I mean, I just put it, so it's plus or minus 6 over square root of 3, correct, class? It's gonna be the threshold point. Square root of 36 is 6, isn't it? Square root of 3 is square root of 3.
3.4641.
I mean, do you agree with me? I'm making sure. What is it?
3.4641.
Plus or minus, correct? Right, now, where is that? And then I'm just gonna talk about it. Remember, the current is Gaussian, which is so nice for me. So that's here to be plus 2.4641.
This is 3.
3.46.
Oh, I'm sorry. Oh, gosh. I'm sorry. So this is plus 3.4641. And here's minus, I don't know how they do it in the book, but I'm going to do it this way. And what I really want is, I want to figure out what the probability that the current is. Now I'm going to show the density function of current. I'm sorry. I shouldn't have even put that coloring there, but that's the demarcation point. Do you agree? Now I take a look at the probability density function for the current, f of I. I'm just going to put it down. You don't need to put this down. It's going to be square root of 2 pi sigma I. Here it's exp. The minus, in this case, it's just I squared because the mean is 0 over 2 sigma I squared. And I put that down there. I know when the mean is 0, it looks like this. And now I get the point. Here's the current value, and this is plus 3.4641. Down here is minus 3.4641. And what I want to do is find the area here. This is what I should have done. Y'all follow me? With me? Bradley, you okay with this?
Yeah.
So what I'm going to do is take twice the area up here. Now just work with me on your calculus. If you didn't do this one, make sure you get the right answer, because these are things that will be troubling if you mess this up. Because it's going to be like, I know how to do it, and my calculator gave me the wrong answer. Well, you don't know how to use your calculator, so make sure you do it. So when I look here, since this is Gaussian, I know I want 2 times the integral from 3.4641 of that density function. I'm going to just call it f of I di from that to infinity, and that would be the probability that I want. Do you agree with that? I'm putting it down twice the upper interval, right? So now, and I'm doing this my way. Go get your calculators, make sure you can do this any way you see fit. I'm going to use the error function because I'm familiar with it. You can take 1 minus the cumulative distribution function, right? Do you remember this? Or you can do it, this is the way I'm going to do it. I'm going to say this is going to be 2, and then that thing is 1 over 2, and this is ERFC, and then I have to take this variable, and I have to say U is equal to I bar, the value of I minus I bar over sigma. Well, I bar is 0, so it's 3.4641 over 2. And then I put 3.4641 over 2 square root of 2. Because remember, with that Q function that I use, I go from that point to infinity. And then I define that, I have to redefine the variable that I'm going to put in the argument of Q, remember, because it's normalized. Just try it on yours, I want to see what I get. So here's what I get. And I'm going to pull out my calculator and do this.
I minus I bar is that number you found earlier? 3.46.
Well, I bar is 0, right? Right?
Yeah.
So, isn't that right, class?
Yeah.
The average value of the current is 0, that's by definition. Hold on. I want to do this one on mine, and please, I don't know if the book's answers right, but I want to make sure we do this right. Is this the question we're curious about? This part?
Yeah,
This is a good part, but I mean, you see the way I'm doing it. You don't have to do it that way, but if you're going to use the cumulative distribution function, you have to understand, take 1 minus the cumulative distribution function at that point, now you get 1/2 of the actual value, because that's only the upper part of the interval, you have to multiply by 2.
Why is sigma 1?
What?
Why is sigma 1 when you calculate for u?
It is,
Oh, it's 2. Okay, I see it.
that's 2.
It's, yeah.
Sorry.
I know.
All right, hang on. I want to just get this. What do I have? I got URFC. 3.464. I do not like these Flex LM licenses. They make me.
Sigma.
.083?
Yeah.
That's,
Is that what you guys got? Did you get that? I mean, you sure?
yeah.
Did you get it? How did you do it?
I did 2 times 1 minus the
The cumulative
CDF.
distribution. Did you use, what's the function actually when you calculate the inspire? Is it C?
It's norm CDF.
Y'all hear that class? There's a lot of you. Do you have that one? Do you have a calculator or not? What calculator do you have?
Let's get inspired.
That's the same one he has, right? You know how to get this? Did you get the right answer? I want to make sure there's no, because this is the problem I have. I can't teach you how to use your calculators, but somebody that knows how to use your calculators can. Did you get it? All right, hold on. Did you get the right answer? Did you get the right answer? You got an answer back? Can you go over and show me? I promise you I'm doing you a favor. This is usually the mess I run into with calculators. Right? Did you get the right answer?
No, I didn't.
Do you have the calculator?
Yeah,
You didn't get the right answer?
yeah, but I thought he's in the wrong.
Yeah. I know. That, some things don't need to be stated. Did you get the right answer?
I know, I think it's 1 minus.
I'll put the answer down. So the answer I got was .083 and it's rounded.
And this was lower. This was versus forward, upper, this.
083.
Maybe.
Okay.
Get it now?
This is 3.46.
Did you get it?
And that's 2.
The normal distribution.
So just like,
Because if you don't know how to do this, you know, on Quiz Friday, you're going to mess up on your calculators, even though theoretically you have an idea.
yeah, now I got it.
Okay. So,
You want me to put it in terms of your calculator?
wait, I think I looked at it wrong.
Don't forget you got to multiply by 2.
Times 2. Yeah, I got it.
Oh, you got it? Did you get it?
Your mean values here.
You got it.
Yeah.
But it looks like a U. So you think it's that U?
I know he used tables.
So
The
you
reason
use
I prefer calculus, that's what you guys are going to use. You're not going to use tables. And a lot of people don't know how to use their own calculators with these kind of things. By the way, you got a statistical package on that, don't you?
I don't think so. Just
I thought
comes.
you had all the stat functions and everything. You can write programs.
Well, there's no like.
You can
I
write.
haven't added anything, but it like comes with it.
It's amazing what they've got on calculators.
You can put Mario on here if you want.
Super Mario, you talking?
Yeah, you jump up.
I've seen that game years and years ago. Little guy jumping around. Italian music.
Can you use zero then?
For I. Wait, no, go ahead. I'm going with you guys along. I'm doing the probability, but I'm not doing with power, right? I'm doing with current. So the current mean is 0. That's the way I'm doing. Now,
In your equation up there, you have sigma t squared. Is this supposed to be sigma of I?
no, it's sigma of I. That's my I, which is the beta.
And it is squared.
Yeah. You know, I want to tell you something too. With the Maxwell-Boltzmann distribution, your calculators may be able to calculate moments that, but in general, the Maxwell-Boltzmann distribution we're going to talk about, there's not closed form solutions for that.
You can just
You
do
gotta
that.
actually do the numerical intervals.
Yeah.
And yours might be able to. That's the reason I was asking that statistical package.
So we haven't, to my understanding, we haven't gotten really to Maxwell Boltzmann.
We're about to,
Okay.
but not yet. I want to do one other thing. Class, I'm just trying to make sure these kind of problems we won't have problems with. And anytime there's a squaring, it always causes problems. Because we can go, depending on the type, if we have a square root of x squared plus y squared is equal to r, and we have f of x is equal to f of y in terms of its shape, both mean 0, then we can use Rayleigh distribution. This case is a little different. This is an I squared problem. Follow? No, just let them help you. I'm telling you this much.
Yeah.
You put this thing off until Thursday night when you think you got it and come in and you fail. I have to beat myself up sometimes because I have a tendency when, especially when I'm tired, to just, I'll get it later. Don't do that. There's a proverb in the Bible I love. It says, "He who loves discipline loves knowledge." I've learned that to be true. If you force yourself when you don't want to, especially when you're exhausted, then you'll get it. If you don't, you had it. All right, next. Wait, you're asking about this. Is there another part? No. All right, I want to do one more in this section just because the last one. You got a good one for me?
The 265.
265? I don't know what it is. I didn't do this one, but let's do it. I mean,
The average speed of the nitrogen molecule.
wait a second. This is Maxwell-Boltzmann.
Yeah, that's a
All right, well, I can bring in Maxwell-Boltzmann distribution. I might as well. I mean, how about, do we have like 2-6.2 or 3? Doesn't?
Let's do the 3.
So this is
Oh,
a
yeah, that's a, what is it?
The Rayleigh probability.
Rayleigh.
Rayleigh probability density function. Anybody else?
Capacitor resistor having resistance of 2
Hold on. We've got a current going in I, and we have resistor R. Go ahead.
Yeah, the resistor is 2 pi ohms,
2 times, okay.
and then the mean value of the current is 2 amps.
I R equal 2 amps. Go ahead.
Fine.
What is this, a Rayleigh distributed current? or-
Yeah.
All right, hold on. So now we've got F of R, of the current itself, or yeah, F of I, if it's Rayleigh distribution, is going to be sigma of I squared. Oh, sorry. That sigma squared is the Gaussian sigma. You remember this? He's saying the current has a Rayleigh or power?
This is a current having a Rayleigh
Okay. A Rayleigh probability is. So that sigma is the sigma associated with the X or Y variation. This is real important because you can screw this thing up. I always put an X here, and it's going to be, sorry. The way he gives, I'm trying to make sure I get this right. I don't know how he does it.
R over sigma.
It's R over sigma squared. I'm doing this. This is the density function, not the integration. So this is going to be the actual I, it would be over sigma of x squared over exp, and here it's gonna be of minus I squared over 2 sigma squared, right? And then we have the F, now this is the Rayleigh, and I'll put an R here, of I, this is the integrated effect, which is 1 minus, and that's gonna be exp of minus I squared over 2 sigma squared. And I better put a sigma of x here, so you know that has to do with the maximum Boltzmann distribution, I'm sorry, the Gaussian distribution, not the Rayleigh distribution. You all with me? Okay. Once I have that, now ask the question.
Find the mean value of the power dissipated in the user.
Okay, here's what I'm gonna do first. They give you this, and in the book, I don't know where it is, they have this is equal to the square root of pi over 2, and I call it sigma x. Do y'all remember me talking about that? Where's this formula in the book? This would be the actual average value of the Rayleigh.
Yeah,
Yeah. Where is it? What formula?
it's,
I think
What equation?
it's gonna be in,
All right, page 8, but make sure you know that. All right, and I might have to give that, because it's easy to forget. You'll mess up with 2 and pi, but remember this one thing, the average value of the Rayleigh average value is greater than the average value, or greater than sigma of x. That's what sure.
Yeah, maybe.
All right. So this one is 2. Now we need sigma x. This is the way I'm going to do it. So sigma of x, this is the Gaussian. Now I'm going to say that's equal to 2, and then invert that, square root of 2 over pi. So I need this value next. You get it?
1.59.
Sure.
577.
1.59. All right. I got that. Now you said they want the mean value of the power. Is that right?
Yeah, it's power dissipated in
Okay. So when I look at this, they want the expected value of the power, which is the expected value of I squared R. I'm just putting it down though, it's the way I would do it. So that's R, since R is a constant, times the expected value of I squared. I hope this is making sense to everybody. The only thing I'm doing is just trying to break it down into the steps. First, define power, right? Then the expected value of the R can come out in front. Maybe I should do it this way, right? Expected value of that, well, that's R times I squared, right? Now that's the mean squared value, correct, class? Please just follow. There's a formula in the book. You can actually prove this if you wanted to with your calculators when you do it. But this is going to be R, and this mean squared value by, since it's Rayleigh here, is going to be 2 sigma, but this is sigma x squared. Remember that. That's the sigma that has to do with the Gaussian distributions, right? I make this point over and over. So R in this one is 2 pi. Did you say that? Yes. And then I have to put 2, and sigma x is that, and I got to square, so that would be what? 4 times 2 is 8 over pi. So it's going to be 2, and then it's going to be 8 over pi. And that should be the expected value of W or pi. And what is that value? 32. But this, the idea is 32 twice, is that right? It's actually a very good problem because it forces you to make sure you get the sigma associated with the Gaussian first. Break that out. If you don't do that, you get the wrong answers. Did you do this with me? What's next? Then I got a question for you.
the probability of dissipated power is less than 4
All right. Probability of less than or equal to 12 watts, greater than 0. How do you think I would do that? How would you?
Yeah.
Well,
Yeah, in terms of I.
yes. Did you do it that way too? Y'all follow me? How many did this one? Just be honest. All right, some of you didn't do it. I'm going to tell you if you did it though.
I'll start locking in. No, I didn't. I'll
You-
start locking in.
You looked at it? Right? All right. These are the ones that people usually fumble. All right? So if I'm looking at this, I always draw these things out. If I want power versus current, right? I always draw this, so it's going to be this, right? This is my RI squared business. So I want the probability that the power is less than 12 watts. Now you can see what I'm going to do. I'm going to come here, but I know the current is what? The current is rarely distributed, so it has no negative part. That's the point I always want to make. Y'all with me? Follow me on this? Real important. That's suddenly okay. So what's this going to be? Well, since W is equal to I squared R, W over R, right? Square root is I. Where's that threshold? Well, 30, you said 36 watts? So it's going to be a square root of 36 over 2 pi. This is 2 pi. That's going to be square root of 18 over pi. What is that? I'm trying to find that threshold point, because then I need to figure out what the area is below. But I think you guys can see. What is it? 18 over pi is what? 18 over pi square root of the whole. 394? Anybody else confirm that?
Yeah.
Okay, now, I got the Rayleigh distribution here, right? So the only thing and remember, that's the value of the cumulative distribution function. So that part of the problem is just going to be F. There is a Rayleigh of, what is that? 2.394. There's 1 minus, you tell me what you get to this. That's 2.394 squared over, that's 2 sigma squared, sigma squared. So I just put 1.59 squared. So it's 2 times 1.59 squared. What do you do for this? Sorry.
Yeah.
Sorry. Minus. My bad. Y'all with me on that? I apologize. Say it again. 0.3127. Is that the answer? I don't know.
Yeah.
Did you get this? Is it right? You didn't get it. These are the fumbles that people will routinely, and it's like, well, that's not a big, it is a big deal, it's wrong. Huh?
I got
Oh,
but
but
your
you're
numbers
looking,
I got.
but this is, but let me just put this up here. This, what I'm looking for is this calculation. F is 1 minus EXP. Here, I'm gonna have minus the quantity 2.394 squared over 1.59 squared. I mean, what you get, just do it in your calculators, this shouldn't be hard. Just looking at that, I can't tell. Huh?
But that, 0.67.
Can you use that? Did you get this right answer?
The
Answer should be that.
Did you get it though?
Yeah.
yeah.
I had like 1.38
Yeah.
on the top
Way
for
over.
where R should be.
I'm sorry.
The is the mean value of R is you get something different.
Wait a second. Wait. This right here, I want to make sure I didn't put something in. For this one, that sigma x is the sigma right there. Isn't that 1.59? Or am I wrong?
Yeah, it's 1.5.
Well, that should be 2 times 1.59 squared, and this I should be associated with that 2.394 if we did that right.
That's what was different.
What is different? What's this value?
We did, yeah, I did 12 over 2.5.
What?
Instead of 36 over
I'm sorry, wait a second. What?
So that we want the probability that, that
2.5. It's let
Howard,
C equals 12, so then on the
Oh.
W equals 12, yeah, equation.
Well, 12, I thought it was 36.
36 was the answer
That was
we got
the
the
average.
previous answer.
I'm sorry. This is 12, this should be 12. My bad, let's do this right. My
And
bad.
that gives you 1.382.
This is 1.382.
Yeah. And then when you put that into.
That's my
other
fault.
stuff,
I wasn't kind of, all right, so this, when you do it,
then you get the answer.
F of I equals, and this is 1.382. 1 minus EXP minus 1.382 squared over 2, and sigma x is 1.59 squared. And that does give the right answer? Is that right? And the answer was 0.3 something? 0.1?
3127.
3127. Confirmed? Looks like that. I have no idea. All right. That's the problem, where it's, you're getting information where something is related to a known density function, a known variable by a squaring operation. The R is just a scalar value. Next thing is Maxwell-Boltzmann. And I'm going to do this. I want to tell you, your calculators may be able to do this, but I'll say this much, that I am not sure. Maxwell-Boltzmann is a very important distribution. It has to do with the actual velocity distribution of molecules in air if they're not ionized and at a given temperature. Let history do this. It's kind of interesting. So if we look at this one, we'll talk about space itself. It has 3 dimensions, x, y, and z, and 3 velocity components, vx, vy, and vz, and they're orthogonal to each other. So when you get the magnitude of velocity, it's going to be equal to the square root of vx squared plus vy squared plus vz squared. Now, something that is not said in the book is if you're going to use this appropriately, you have to assume that v, the actual distribution of v of x is the same functional form as vy of vy as the same functional form of vz of vz. In other words, these things have to be identical. They also have to have, and this is where you get in trouble, vx mean has to be vy mean has to be vz equals 0. Now that's not true if you're talking about ionized molecules. Just let me finish my thought and you'll understand why. So if you have ionized molecules and you put an electric field in there, that electric field will skew the distribution of either x, y, or z component, or whatever direction it's in. It'll skew it and you won't get an average. This is where these things get complicated in a hurry. But for this case, if you assume this, then you get something that's called, and it's the magnitude only of the velocity, but it is called the Maxwell-Boltzmann distribution. And this is only true for positive values of v. In here, you can mathematically prove this. But the way he does it, try to find the actual formula for this in the book, but it's going to be similar to Rayleigh, only it's going to be an actual value of v squared out front. This is not one I have committed to memory, by the way, but I could use it. I have just so here, this is equation 2-33. And what he's doing, he's not putting a constant numerical value, he's going to put square root of 2 over pi, and then it'll be v squared over sigma squared. Put sigma x squared here. Sigma x, this is Gaussian. You should be done or I'm sorry, cube. Sigma x cubed. exp to the minus, and it's going to be v squared over 2 sigma squared, and this is true for v greater than or equal to 0, and v is a magnitude always. So then he's going to show you a few things. First thing he's going to say is, if you were to get the expected value of this, v times just the expected value of the velocity, or the mean value, he says that integration is difficult. It's not tabulated. Your calculators may be able to do this. I don't know that for sure. This is called the Maxwell-Boltzmann distribution, or something to that effect. And it's a three-dimensional distribution. Rayleigh is two-dimensional. This is three. Anyway, in the book, he's going to give you this. I would never ask you to remember this one. It's 8 over square root of pi times sigma, but that's sigma x. So make sure on these things you realize that that variance or standard deviation has to do with a Gaussian distribution. It's very, very important to keep that in mind. Y'all with me on this one? So that's the expected value. Then the mean squared value of velocity, which is kind of interesting. Is 3 times sigma x, and this is going to be squared. Now I'm going to mention something about this. He shows that this is right in the middle of page 83. He doesn't label this, but this is something you think about. The way I think about this. Remember, this is Maxwell-Boltzmann three-dimensional, right? I'm just going to put down 3D. If you think about the expected value for the Rayleigh random variable squared, or the mean squared value for Rayleigh, which is 2D, it's equal to 2 sigma x squared. With me? What's the expected value for the Gaussian random variable x squared? Just sigma x squared. Y'all with me? So the higher the dimensions, it goes up linearly. This is just something to notice. And I want to say something with abstract mathematics, and mathematics is some of the stuff they do in really high-level astrophysics, physics, where you get distortions of space-time. You get a fourth dimension of time. And you get, it's way beyond the scope of this class. If you looked at the expected value of something that included time as an axis, it would be 4 times sigma x squared. Now that's way beyond the scope of the class. But you have to understand this dimensionality, like we think of orthogonal x, y, z. Can't have more than that. Wrong. Orthogonal axes don't have to be something that have a physical interpretation. You can have any number of orthogonal coordinates, right? It just means the projection of one coordinate has nothing on the second coordinate. Like if you have x and y. If I have any value of y and I project it onto x, I mean, I call it the shadow of if you think about it, that x, this y, you got a sun right above us. There is no projection onto the x. They're called orthogonal. Ax dot ay is 0, basically. The unit vectors dotted are 0. Ax dot az is 0. Well, ar dot a phi is 0 and cylindrical. And I can go on. There are technically 10 separable coordinate systems. This is hard to get a handle on, but there's a book by Spencer and Moon that I have. I should send this to you just for reference in case someday you got to dabble in this area. There are 10 separable coordinate systems that have to do with reality as we know it, x, y, and z. You can have cylindrical, you can have spherical, you're exposed to those. You can have proloid spheroid, looks like eggs. You can have all these things. Those are dimensionalities that can be physically interpreted in reality. Now, orthogonal dimensions there can be any number. You could have ax dot ay is going to be 0, AZ dot AX is 0, but then you could have an AK, as long as you define it such as a dot product of AK dot AZ is 0, you can put any number of orthogonal dimensions even though they don't have a physical interpretation. This is where it gets bizarre. But some of that stuff's useful if you're going to take time out of the equation. It's called Minkowski space, well beyond what we can deal. Remember how Einstein basically said the only thing that's constant in the universe, and this is actually true, proven, is the speed of light in any reference frame. It never changes. Gravity itself, as we see it, is kind of an illusion because the whole idea of general relativity, the way it's is that light being a constant velocity in any reference frame is the secret to getting all these values. And gravity itself is just they call it it's an energy puckering of really the space itself, and it's hard to expand this. Remember down here, there's an acceleration on you, right?
Mm-hmm.
Well, I'm not accelerating. No, you're not moving in this dimension, but what's the acceleration? It's m times a, right? So I have an acceleration pulling me down. That means I'm in an accelerated reference frame. If you're in a non-accelerated reference frame, it means there is no force acting on you. All right? So if you think about this, if you drop a ball in a perfect vacuum, say the Earth, as it's falling, it's in a reference frame that is different from the reference frame it's falling through, if that makes sense to you. And the speed of light will be the same in both. This gets very hinky. If anybody had modern physics, you might have.
Bits and pieces.
Huh?
And bits and pieces in physics too.
This is a very hard concept.
Time expansion and length.
Well, it's really length contraction and time dilation. But there are things that go on that are extremely hard to get a handle on because we've been exposed to the physical world. But some of you, as engineers, are going to be dealing in that area with all this crap going on with, I tell you, the more I read about what they're doing in space, the more you're going to have to understand that. And I'm just throwing some tidbits out here to be aware of. So anyway, back to this stuff in the Maxwell-Boltzmann distribution. Remember what I told you? One dimension, sigma squared. That's the mean, or that's the mean square. Or it's going to be the mean squared value, as long as you have an average value of 0 for Vx, Vy. 2 dimensions, 2x squared, or 2 sigma x squared. 3 dimensions, 3 sigma x squared. 4 dimensions would have that, and I don't pretend to even try to explain that because I don't deal in that world. But you at least should be aware of it. Dimensionality has to do with the energy's average value going up for a known profile, one of the dimensions, a known statistical variation. Enough said about that. So I want to talk about one thing, and this is the kinetic energy and the expected value of kinetic energy. And this is kind of important that you are aware of it. So when you talk about energy, if you've got a particle of mass m that's moving with a velocity v, the classical non-relativistic energy is going to be equal to 1/2 mv squared. I hope you all understand it. That's just the energy. All right? E. Now, he uses small e. If you look at the expected value of the energy in the molecules in a gas, you get the expected value of this, so 1/2 mv squared, and that's simply 1/2 m times the expected value of v squared. And that happens to be, and I'll put it up here, that's 1/2 m, and this becomes 3 sigma. That sigma is of the Gaussian distribution of either Vx, Vy, or Vz squared. And now that should make sense to you, right? We're talking about one molecule, and we're looking at the actual energy of one molecule is 1/2 mv squared. Do y'all remember 1/2 mv squared from energy? Non-relativistic. You get near, you talk about relativistic stuff, everything I'm saying doesn't matter. Now we get into totally different distributions, but that's what astrophysicists like. Do you know this guy Neil deGrasse Tyson?
Yes.
All right, so he's great at explaining things in a way that you kind of can appreciate. The higher level guys from MIT, if you watch these guys, it's like, huh? You know, really, honestly, like, n-dimensional space means nothing to me in terms of visualization. Three-dimensional, I think I can handle. Three-dimensional, throw time in, kinda. When you talk about time dilation and all that stuff, it gets really to a point where I have no idea what you're talking about real quick unless you go through and parse it. But Tyson's good at this. Anyway, for this, remember, he's good at this kind of stuff. Astrophysicists deal with this crap all the time. So when I look at this, that is the average energy of one molecule in a gas, and it's a monotonic gas. It's only one type of particle, and they're bounced around perfect elastic collisions. That is equal to 3/2 kT. Now the K is Boltzmann's constant. 1.38 times 10 to the minus 23rd. And gosh, what is it? Joules per watt second. Now you don't need to remember this. I'm just trying to tell you there's a universal constant. Yeah.
I think it's
Equation, is that, supposed to be V?
This is V squared.
V squared.
Yeah, it's the expected value of V squared.
joules per Kelvin.
Watt second is Kelvin, isn't it?
Yeah, it's watt second per Kelvin.
Wait. This is watts, watt seconds per degree Kelvin? Is that what you're saying?
Yeah.
But that is, see, a watt second is energy, it's a joule.
Yeah.
Watt seconds per degree Kelvin,
Right.
right? Okay. I think that was the same thing I wrote.
You had WS on the bottom. You had
Oh, okay, I got you, right. I'm sorry, you're absolutely right. Now, I'm gonna level with you. I only deal with K, this constant, when I'm dealing with radar stuff, because it has to do with noise calculation. So I have to use this all the time. T is gonna be the temperature in degrees Kelvin. Degrees Kelvin, the 0 degrees Kelvin, nothing moves. There is no such thing as 0 degree Kelvin in the universe, theoretically. Because theoretically, you can never get to a point where nothing moves at all, theoretically. I'm just telling you this. So they found this out. That's for one molecule. Do you remember the concept of mole? All right, so what is that, 6.023 times 10 to the 23rd particles is 1 mole of a gas. So basically, you all with me on that?
Avogadro.
Yes. And if you're a chemistry guy, you do live in that world. I mean, gas physicists, chemists, stuff like this, gas chemists. Anyway, 23rd, come down here. This is something real important because that gives us, that's useful for energy calculations in gases and stuff like that. When you had chemistry, didn't you guys do this stuff or not?
Yeah. It was a check the box class though for me.
What's that?
It was just a check the box class for me, so I didn't.
Well, I hated chemistry when I took it because there's so much memorization. Then in graduate school, I had crystal chemistry, and the whole thing came together. It's like, oh my gosh. Everything in chemistry, by the way, is based on electrostatic attraction and repulsion. Whether you know it or not, Linus Pauling is a guy that wrote this. He got 2 Nobel Prizes, but one was for peace, the other is for his nature of the chemical bond. He showed that when you talk about chemistry, we always we draw these beautiful pictures, we got structures and all rings and all that crap. Well, the real thing is this. There's an electrostatic attraction or repulsion, all these things. And there's allowable energy states because these things are moving around, electrons are moving around. And they have to move such that the wobble in them is exactly 2 pi times n, where n would be the number of circulations they get. So you can actually go through, it's amazing too. And if you use Maxwell's equations with electrostatic repulsion and attraction, you can get all the stuff that has to do with the trajectories of the electrons, the allowable, and all that other crap. And a guy named Dale Grimes, who was a professor I had, did all that stuff. And what blows your mind is, if you understand that, then all the stuff, they talk about electronegativity and all this stuff, it starts making perfect sense. But the way I had it, I just memorized cajillions of bits of information, things that you just join. Anyway, back to chemistry. Or now back to this. So I'm just mentioning this stuff. I'll say this, he gives you, there's a couple of open statements in there that to calculate this, use this to calculate the mean and all that stuff is beyond tables. Now your calculators might do it. When I was doing plasma physics in graduate school, this is the basic distribution you get of something without an electric field in it. Now when you put an electric field in it, now you get a skewed value for the average velocity, either x, y, and z, and this distribution is perturbed. And you got to calculate what are called moments of it. For instance, the mean value would be take v times that and then integrate it over all possible values. The mean squared value, you need the mean squared value to get 3/2 kt right there. You need that, and you need all sorts of different things that you use for plasma physics that's way beyond this class, but I was very familiar with that thing when I was in grad school because my master's work was working around plasma. And I had a lot of courses. I want to mention uniform too. I didn't mean to talk that much about it, but it fascinates me. I don't want to tell you about this dimensionality stuff. Anytime you talk about more than 3 dimensions, you kind of lose me. Have you ever heard of 4 dimensions or 5-dimensional space or anything like that?
Yeah,
Yeah.
Where'd you hear about it?
calculus 3.
Oh, really?
Yeah, hyper surfaces.
Yeah. Okay, good.
YouTube.
YouTube.
Yeah. 3 a.m. You can't go to sleep. YouTube video.
You know where I read about a lot of stuff? There used to be, there's a magazine called Omni Magazine. I don't know if it's still around anymore. Anybody ever hear that? It came up with, it was like pseudoscience. They take stuff that partially true, partially we're guessing. And they come up with the most bizarre stuff, like, you know, this is with aliens and stuff like that.
It sounds like the History Channel at 3 in the morning. They'll have you believe it.
Yeah, Ted has a podcast called Star Talk. He goes in depth with this. I don't know.
Star Talk, the guy from, the guy, Stargazer, whatever, isn't it the guy from Florida, old guy, or not? No? Okay, wrong guy. Stargazer was something I was used to when I was younger. Okay, now, next thing is uniform distribution. Now this is the one, it means this. This is a uniform distribution, and I'm a little low on time. So if you have a value x1 and x2 here, and you got some f of x, you can see this is assuming it's constant. The height of this thing is just going to be 1 over x2 minus x1. It has to be. They're showing this is the distribution function. This is called a uniform distribution. It means the probability function never changes. Now, one look at that, you can pretty much tell if I want the expected value of x right here, well, it's integral of f of x dx from x1 to x2. Take one look at that. Well, if we integrated from x1 to x2, we would get really x dx, right? X squared over 2. Why don't I just do this real quick and then I'll show you the rest of it. So this is listed as x bar. Here I take the density function, which is 1 over x2 minus x1, and then I integrate x times dx, which is x squared, so I get x squared evaluated from x1 to x2. Here I get 1 over x2 minus x1, and then I get x2 squared minus x1 squared. I'm going to just show you the trick real quick. Y'all with me, class?
What's that subscript for the big F for the distribution?
This
The subscript on the other side.
here,
Yeah. F. Or is that E?
that's xe. That's expected value. I'm so sorry, it's expected value. That's what this is. All right. Now, if you look here, this is just something you pick up. x2 minus x1 times x2 plus x1 is what? It's x2, right, squared minus x1 squared. Y'all follow me? Just follow me on this one so you understand why. Take one look at that. I got x2 minus x1 down here, and I got x2 minus x1 times x2 minus x1 on top. The only thing is, it's going to be what? This is over 2. It's going to be x2 minus x1 over 2. Follow me? Take a look. Integrate the x dx is x squared over 2, right? Evaluate the upper, it's x2 squared over 2 minus x1 squared over 2. The density function is 1 over x1 minus x2. But you gotta take this and factor it so you can cancel that lower term and you get this. This is the only thing they're doing, and he shows it. More importantly, if you just look at this, that's the density function. You see it's dead center, it's x1 plus x2 over 2 has gotta be the average value. You with me on this for a constant? Just look at that. You don't need any kind of math, right?
I think it should be plus right there.
I'm sorry, it is plus. The x1 minus x2 cancels the x1 minus x2 on top, and it results in x2 plus x1. I'm very sorry about that. You all with me, class? Thank you. All right, now, next part of this, all right, is what is the expected value of x squared? This is a little trickier, but I'm just going to show you what comes out. So this is going to be the integral. Let me do it this way. x2 minus x1, I'm just going to call delta x. We don't have to prove everything, but you can see this. So now this expected value becomes the density function, which is 1 over delta x. I'm glad it wasn't car insurance this time. x1 over x2, and here it's x squared dx. I hope you all follow me this, right? Just the definition. So this becomes simply 1 over delta x. And then I'm going to get x cubed over 3, evaluated from x1 to x2. You have to trust me on this part. So now I get this, and I go ahead and put the variables in. So I get 1 over x2 minus x1. Then I have a factor of 3 here. And then I get, that should be x2 cubed minus x1 cubed. Y'all follow me? Remember how I did this thing up here where I basically said this is true? Now if you take this, square that and square this, you're going to get cubes there. I'm just going to tell you, you're going to get the cube crap. At the end of the day, when you look at this, I think I'm about out of time, you're going to get this because, let's see. When you do this, you're going to get, what he's going to have it down there, I believe is going to be x2 cubed, I'm sorry, x2 squared minus x1 squared, and then it should, if he has the factoring, I'm not sure if he has factoring here or not. It should be x2 over x1 cubed over 12. Wait a second. That's not right. Hold on for 1 second. I don't think what I'm thinking is right. I want to make absolutely sure. Yeah, that's over 12. That's right. Wait a second. He doesn't have, he has sigma x squared. This is what he has. That's what I'm saying. He has sigma x squared is going to be x2 squared minus x1 squared over 12. But then for the expected value of x, this is what it is right there. And you can factor, I believe you can factor this thing out. You get x2 squared minus x1 squared, and then this one. Yeah, that will cancel, I believe, on top. I didn't do this one entirely, but this is the one thing he's going to have that's important to see. And he has a wrong answer also. So write that down, and let me just tell you this much. So in his book, if and I'm trying to do this in a way that's meaningful here, on page 89, middle of the page, he's going to have the variance for something, and it's wrong in there. and he says if it's a uniform distribution. Now, I'm going to give you problems that have to do, and the final distribution I want to talk about. Give me 1 second, and I'll do it. It's called the exponential distribution, and this is on page 92, and it starts there, but this is a straightforward one. So I just want to mention this one. You're going to see you can use these things, and it's fairly easy to get anything from them. This one's easy. I mean, if you're trying to get anything from a uniform distribution, it's a very easy integration stuff. If you have the actual values, you don't have to worry about some sort of a formula like that. But let me just finish this. I want to get to this. So the exponential distribution is going to be this. It's f in here of t. He's going to do this in time. And he's going to say it's equal to 1 over tau exp of the minus t over tau. So if you look at this distribution, it's kind of a common one. It's saying here's the value of 1 over tau, and this is f of t here versus t. That's the value, and if you integrate this thing from 0 to infinity, you get 1. Trust me on this. So try to follow me on this. The exponential distribution appears tons of places, from failure rates, expected failures, and stuff like this. What it's saying, say this is a failure rate. The probability of failure of the part from 0 to forever, the probability of fails is 100%. The probability of it failing or passing, however it's defined, from 0 to some t1 is just going to be the integral of this from 0 to t1. You all follow? Well, what is that? Well, the integral of this f of t dt from 0, and I'm starting at 0, and it has to some value t1. Well, that's going to be the integration of this is going to be what? Minus exp of t from 0 to t1, and that's really going to be 1 minus exp of the minus t initially over tau. Can you all follow me? That's the probability of the event occurring less than or equal to t1. And this should be t1. And you can see as the t1 goes to infinity, it's 100% sure something happened between 0 and infinity. Now, the one other thing about these things is, say you got something that fails at t1. We know, I mean, say you want the probability it's going to fail between 0 and t1, so you can get it. And then what's the probability it's going to fail from t1 to t2? From here to here. So looking on this class? It has nothing to do with this part in terms of the probability it fails from here. Only the distance from here to here. That's the only thing you care about. Does that make sense to everybody? So it'd just be equal to, the probability it fails from here to here would be 1 minus, and it would be exp to the minus t2 minus t1 over tau. Only has to do with the difference. First failure, this is the first failure here. The probability it fails between here and here has nothing to do with this distance or anything related to this. Only the distance between these 2 points. I hope I made myself clear on that. I'll give you some problems in this. Did the shear cover this exponential? It's very useful and happens all the time. I know how to time sorry for this. I tell you, I don't know what it is. Maybe it's fast. Maybe it's something new. We're not even. I don't know the questions today. Okay, so quiz on Friday, a logical question. What's it on? Sections. It's going to be on section 2.5, 2.6, and you should know the uniform distribution because that was even the last one, right? Okay. Stuff like that. I'll do some more problems. And then what I'm going to do, I'm not going to ask you actual Boltzmann stuff. I'm going to do conditional probability, which is section 2.8, I believe, in this book, because I want to use, this chapter is actually pretty good for nailing down some ideas. It is to me. And in 2.9, or 2.8, pardon, he has conditional probability. 2.7, he's got exponential, he's got delta distributions, things that I think we can talk about and figure out. But the conditional probability is really interesting, because here, remember we had P of A given B? Now we're gonna have that type of stuff happen, and we're gonna do a lot of it. And I might add that, I'll try to make the problems more applicable to classical computer engineering. But then, I may be going to the other book, actually I'm not sure, for some problems, but I'll be sure I state the problems and solutions for you. Okay. See you on Friday. Has anybody seen Blake lately?